Have you ever looked up these two views? One elegant, geometric, cosmic, the other messy, chaotic, subatomic. That's the Holy Grail. A single theory that explains everything, from falling apples to exploding stars. Physicists call it the unified theory. And this book? It's about that search. Why time? Time, it's something we all feel but can't touch. We measure it in seconds and years, but we don't fully understand what it is. We know it's always moving forward, yet we don't know why it moves at all. Why did time begin? Will it end? Can it flow backward? And what happens inside a black hole, where time might stop completely? These are not science fiction questions anymore. They are real, mathematical, physical inquiries, and they take us to the edge of what science knows. A warning and a promise. Now, let me warn you, this journey won't always be easy. We'll encounter curved space, singularities, quantum uncertainty, and particles that appear out of nothing. But stay with it. Because once you begin to grasp the shape of time and the story of our universe, even just a glimpse, it changes the way you see everything. Not just the stars and galaxies, but life, meaning, and your own place in it all. So whether you're a curious student, a casual thinker, or someone who just wants to understand the cosmos a little better, this book was written for you. Let's begin at the very beginning of time itself. Chapter 1. Our picture of the universe. Let's start with a simple, timeless question. What does the universe actually look like? Not just what we see with our eyes, but what it is at the deepest level. When we look around, we see a sky full of stars, planets slowly drifting, galaxies swirling millions of light years away. But for most of human history, our ancestors believed something very different. Ancient beliefs. Earth at the center. The earliest models of the universe were built not on telescopes or experiments, but on intuition. People believed the Earth was flat, that the sky was a dome, that the sun, moon, and stars revolved around us. In many ways, it made sense. After all, the Earth doesn't feel like it's moving. The sun does appear to rise and set. To ancient eyes, Earth seemed like the solid center of everything. But then came a few minds willing to challenge that idea. A shift in perspective. Copernicus and Galileo. In the 1500s, Nicolaus Copernicus proposed something radical. What if the Earth is not the center? What if the sun is? That idea was dangerous. It was denied, fought, laughed at. But it sparked a revolution in thought. Later, Galileo Galilei, using a primitive telescope, looked at the night sky and saw something shocking. Moons orbiting Jupiter, mountains on the moon, phases of Venus. These weren't just discoveries. They were cracks in the old picture of the universe. Proof that we are not the center of it all. The universe as a machine. Newton. Then came Isaac Newton, the man who turned the heavens into mathematics. With his laws of motion and universal gravitation, he gave us a picture of the universe as a giant machine, precise, predictable, and elegant. He showed that the same force pulling an apple to the ground also holds the moon in orbit. It was a vision of perfection. Planets moving in ellipses. Time flowing like a river. Everything explainable through reason. But even Newton's clockwork universe had limits. Cracks in the machine, Einstein and relativity. Fast forward to the 20th century. Albert Einstein looked at light, space, and time, and realized something profound. Time is not fixed. Space is not flat. Gravity is not just a force. It's the bending of space-time. Einstein's theory of general relativity showed us that massive objects, like stars or black holes, actually warp the fabric of space and time around them. Imagine placing a bowling ball on a rubber sheet. It sags. That's what gravity is, the curve of space and time caused by mass. And this meant time could run faster or slower depending on where you are. A clock near a black hole would tick differently than one in open space. Let that sink in. Time itself is relative. The quantum world. Chaos beneath order. But on the smallest scales, atoms, particles, and energy blips, Einstein's model breaks down. Enter quantum mechanics. This theory tells us the universe, deep down, is fuzzy, uncertain. Particles don't follow clear paths. They exist in probabilities. Things can pop in and out of existence, and the act of observing something can change what it does. It's a world where logic doesn't always apply. Yet, the math works. Now, here's the problem. Einstein's theory describes the very big, galaxies, gravity, and time. Quantum theory describes the very small, particles, atoms, and energy. But no one, not even today, has a theory that fully explains both. That's the great mystery. The reason A Brief History of Time exists. The search for a theory that unifies the universe, large and small, seen and unseen. So, what does the universe look like today? Today, scientists believe the universe began with a Big Bang about 13.8 billion years ago. From an infinitely small point, space itself exploded outward, and it's still expanding. We live in a universe of galaxies, stars, planets, black holes, dark matter, and dark energy, most of which we cannot even see. And yet, we know it's there. Not from pictures, but from patterns, from echoes, from mathematics that fits together like a puzzle. So where does that leave us? Tiny beings on a pale blue dot, trying to understand a cosmos of unimaginable size and complexity. And yet, we've come far. From myths about sky gods to black holes and quantum foam. This is where our picture of the universe now stands. And the journey ahead only gets deeper. Chapter 2. Space and Time. Imagine you're sitting in a quiet room. You look at your watch. It ticks forward, second by second. To you, that's time. Now imagine someone speeding past you in a spaceship at 90% of the speed of light. For them, time is also ticking, but not at the same rate. In fact, time is moving slower for them than it is for you. Sounds impossible? It's not. It's a consequence of one of the most revolutionary ideas in science, Einstein's theory of relativity, the illusion of absolute time. For centuries, people believed that time was absolute, that no matter where you were in the universe, it ticked the same for everyone. But Einstein showed that time is not a universal river flowing at a constant speed. Instead, it flows differently depending on how fast you're moving, or how close you are to massive objects. This is called time dilation. The faster you move, the slower your clock runs, compared to someone standing still. And the stronger the gravitational field you're in, the slower time passes. You might not notice this in daily life, but GPS satellites orbiting Earth run on a different time than clocks on the ground. And without correcting for relativity, GPS wouldn't work. This is not science fiction. This is the real nature of time. Space and time are one. But Einstein didn't stop there. He proposed something even more stunning. Space and time are not separate. They are part of a single four-dimensional fabric, space-time. Think of the universe not as a stage where things happen, but as something dynamic, something that bends and curves in response to mass and energy. When you place a heavy object in space-time, like a star, it distorts the fabric around it. Other objects, like planets, move along the curves of that distortion. That's gravity. It's not a force pulling things. It's the shape of space-time telling matter how to move. The speed of light, a universal limit. One of the most crucial elements of this theory is the speed of light. It's the ultimate speed limit of the universe. Nothing can travel faster, not light, not information, not gravity. The faster you move, the more energy you need, until you hit a wall, the speed of light. At that point, time would stop. Mass would become infinite, and you'd require infinite energy to keep going. This means there's a built-in limit to how fast we can go, and how far we can travel through space. But there's more. Because if space and time are linked, then moving through space affects how you move through time. The bending of time. The implications are mind-blowing. Imagine a massive star collapsing under its own gravity. It becomes so dense that it curves space-time so much that nothing can escape, not even light. This is a black hole, and near its edge, called the event horizon, time slows to an almost complete stop. If you stood just outside a black hole and watched someone fall in, you'd see them slow down, freeze, and never fully cross the horizon, from your perspective. But for the person falling in, it would feel normal. They'd fall straight through. This is one of the most bizarre and beautiful consequences of curved space-time. The expanding universe. Now take that same idea and scale it up to the entire cosmos. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, and the farther they are, the faster they're going. That means the universe is expanding, which implies something shocking. If you reverse time, the universe must have started from a single dense point, a beginning. This was the birth of the Big Bang Theory, the idea that time, space, and matter all came into existence in a single moment. Before that, there may have been no time at all. Let that sink in. Time itself has a beginning. What does this mean for us? When you hear phrases like time is relative or space is curved, they may sound abstract, but they define our everyday reality, from how we age to how we navigate with satellites. Understanding space and time isn't just about stars and physics. It's about knowing the stage we live on. It's about understanding how we exist in a universe that's far more flexible, dynamic, and mysterious than it seems. It's about looking beyond the clock and asking deeper questions. Can we travel through time? Can we bend it? Escape it? That's where the rest of this journey takes us. Chapter 3. The Expanding Universe. Imagine rewinding time. Galaxies pull back. Stars vanish. The fabric of space shrinks until everything, space, time, energy, matter, collapses into a single point. This is not imagination. This is what science tells us about the origin of our universe. Hubble's discovery. The universe is growing. In the early 20th century, astronomers thought the universe was static, eternal and unchanging. Even Einstein believed this, and he added a cosmological constant to his equations to force the math to support it. But in 1929, everything changed. Edwin Hubble, using a telescope on Mount Wilson in California, observed that distant galaxies weren't just out there. They were moving away from us. And not just slowly. The farther a galaxy was, the faster it was receding. This meant one thing: the universe is expanding. That discovery rocked the foundation of cosmology. Because if everything is spreading apart, it must have once been together. The Big Bang, a beginning in time. This led to the development of the Big Bang theory, the idea that the universe began as an infinitely dense point, then exploded outward in a massive expansion. Not an explosion in space, an explosion of space itself. In the earliest moments, less than a trillionth of a second, the universe expanded at unimaginable speed in a process called inflation. Time began. Space unfurled. Energy and matter formed. Laws of physics came into being. It's the ultimate reset. Before the Big Bang, we don't know what, if anything, existed. Time itself may not have existed. And without time, cause and effect break down. So asking what came before the Big Bang might be like asking, what's north of the North Pole? Evidence of the Bang skeptical? Good. Science demands evidence. And the evidence is solid. 1. Redshift of galaxies. As discovered by Hubble, everything is moving away, like raisins in rising bread. 2. Cosmic microwave background radiation, CMB. Discovered in 1965 by Penzias and Wilson, this is a faint glow left over from the early universe, a literal echo of the Big Bang. 3. Elemental composition. The ratio of hydrogen, helium, and lithium in the universe matches what the Big Bang model predicts. Together, these form a powerful case. We live in a universe that had a beginning and is still changing. What's happening now? So where are we today? The universe is still expanding. In fact, it's accelerating. That discovery was made in the late 1990s, and it stunned the scientific world. Why is it accelerating? What's pushing galaxies apart faster and faster? We call this mysterious force dark energy, but no one truly knows what it is. It makes up about 70% of the universe, yet it's invisible and unexplained. It's as if the universe has a built-in stretch, and it's speeding up. What will happen in the future? There are theories, the Big Freeze, where galaxies drift so far apart that stars die and the universe grows cold and dark. The Big Rip, where dark energy tears everything apart. Galaxies, atoms, even space-time itself. Or perhaps a cosmic cycle, where expansion eventually slows, collapses, and restarts with another bang. We don't know yet, but what we do know is this. The universe has a history, and it's not over. The power of understanding. You might be wondering, what does all this mean for me? We are tiny, atoms in a vast, accelerating cosmos, and yet, we are the universe becoming aware of itself. We've gone from ancient myths to modern physics, from staring at stars to measuring the curvature of space and the stretching of time. All because we dared to ask big questions. All because we wanted to understand. The story of the universe isn't just out there. It's our story too. Because we are made of stardust. Literally. The atoms in your body were forged in stars that lived and died billions of years ago. So when you look up, you're not just seeing light. You're seeing memory. You're seeing your origin. And maybe your destiny.